Having laid down the groundwork for the formation of the solar system, let's talk about where different types of planets actually form within the solar system itself, and finally talk about the age of our solar system.
So there are really two types of planet in our solar system, the gas giants and the terrestrial planets. The gas giants are often alternatively called Jovian planets, Jovian meaning Jupiter-like. The terrestrial planets are the rocky ones. So the inner parts of the protostellar disk were basically hotter than the outer parts. You were closer to a forming star or a recently formed protostar when you were towards the center. And rock remained solid at much higher temperatures than ice. So we ended up with what we could refer to as a segregated solar system. A solar system where the ices and the icy rocky balls were to the outside and the simple rocks was more towards the center of the solar system. So how did planets form at all? Well, planets form around some core. You need some kind of nucleation site, some small object for a planet to form around. And you can think of planets as being like snowballs in a cartoon. If someone takes a very small snowball and rolls it down a hill in some kind of Warner Brothers cartoon, by the time it gets to the bottom of the hill, it's an enormous snowball. And that's kind of how planets formed. They swept out their areas and they picked up material along the way, and a small rock got bigger and bigger and bigger. So in the inner solar system, the temperature was high, and only rock and metal can condense. In the outer solar system, the cold temperatures allowed ices to be in existence. So ices, metal, and rock all sort of bound together to form all the various objects in the outer solar system. So you have more complex, icy, rocky bodies in the outer solar system, and you have more simple rocks towards the inner. And this figure is really showing everything we've discussed so far. So here we have a molecular cloud, a protostellar cloud, which is forming and condensing down to form a disk. Conservation of angular momentum, collisions between the particles give you a disk. And it winds up heating up, and you end up with a lot of heat and energy at the center. So this is where the star would be born. So this is where the sun is born in our system, and the planets will form out in the disk. So because hydrogen and helium can stay gaseous on the inside, they won't be part of the makeup of the bodies in the inner solar system. These will be very rocky bodies that survive very close to this forming star. As we go further through the disk towards the outside, the cold temperatures will allow ices to exist, and it's out here that you'll find icy, rocky bodies. So what will happen is, as I said before, these objects will start to snowball. So here's our solar system, still very hot, still full of material, and these planets will circulate in their orbits around the central star. And as they go around the central star, they'll pick up material and slowly accrete, as we call it. Accretion means to gain more material. And then you'll have the Jovian or gas giant planets on the outside doing the same thing. They will go around in their orbit and they will pick up all the material in their orbit and add it to themselves. So each one of these planets is clearing out its own orbit and picking up material. And then finally what will happen is the star will switch on and full-blown fusion will occur. So a lot of energy will be generated from the star, and then that will blast what we call the solar wind. It will throw out charged particles from the surface of the sun, and those charged particles will pick up any remaining gas, debris, and will get rid of it. So all the gas that was left over in the solar system will be thrown out by the solar wind, by the charged particles exiting the star. And that will create nice empty space between each of the planets. Obviously there are a few particles in here, but it's very close to vacuum, just a few particles per cubic meter. The solar wind has cleared away all the gases, and there may just be a few rocks and ice left over. But that's how the solar system goes from a relatively low density cloud to a higher density disk to a system with a star at the center and then planets neatly placed in orbits around it. And you'll have your icy bodies towards the outside, and you'll have your rocky bodies towards the inside. So we can actually define a specific point beyond which we have rocky or icy bodies. And we call it the frost line, which isn't very imaginative, but it's very descriptive. And here's that frost line. So here's a protostar forming at the center of this disk, and it's pumping out radiation, and it's heating up all the particles. Now, as the temperature is going to fall off the further away you get from the star. So put your hand towards the old-fashioned light bulbs, which used to get quite hot. As you get further away, you feel less and less heat. And that's exactly what's going on here. So we can define this point in the disk that we call the frost line. Inside that frost line, rocks and metals will be able to condense, but hydrogen compounds won't be able to form ices because it's too hot. Outside of the frost line, you'll have rocks and hard and metallic material, hard and metallic stuff, and you'll also have ices. So beyond the frost line, you'll have bodies with more ice in them. Inside the frost line, you'll have much rockier bodies. And remember, any ices that are formed on the Earth today are usually a result of the atmospheric conditions. So inside the frost line, too hot for hydrogen compounds to form ices. Outside, cold enough for lots of ice to form. So the frost line is really the point at which you're switching from rocky planets, to gas giant planets. Inside the frost line, rocky planets dominate the solar system. Outside the frost line, your gaseous or icy bodies will dominate the solar system. And go far enough out, and you'll just have ice, such as comets in places like the Kuiper Belt or the Oort cloud. So outside the frost line, gas giants and comets. So as far as gas giants work, gravity draws your planetesimals together. And when I'm talking about gas giants are huge. So you start with a small planet, and they're going to accrete material. So the assembly process of a planet is referred to as accretion. And that's what we were talking about with the snowball effect. You're going to pick up more and more and more particles until you're left with a rather large planet. And in the case of something like Jupiter or Saturn, it must have picked up a lot of ice and a lot of gas. So this is the kind of thing that's going on. Inside here, this is very close to the sun. You don't have any real flakes, as it's stated here in this animation, but let's call it particles of rock or of ice. Come into beyond what we call the rock-metal condensation line, and beyond it you can have rocks and you can have metals. So in this region, this is where you just have rock and harder material. And what will happen is that will literally be like the snowball we discussed. Particles will run into one another and they will get bigger and bigger and bigger until eventually you formed what we would call a planet or an asteroid, depending on the size of the body. Going out to the frost line, so remember, here's the sun in the center, this is where the rocky material is aggregating, and now we're accreting out here, we're accreting bits of rock and ice. And if we look at a lot of the moons of Jupiter and Saturn, they're both rocky and icy. Something like a comet would likely start off with a rocky core, a very small rocky core, and then pick up ices as it goes. So the gas giants were the outer planets, and these increased in size as they picked up hydrogen compounds, and those hydrogen compounds condensed to give you ices. The outer planets basically accreted and held on to more hydrogen and helium because they were huge. Hydrogen and helium are very light, very tenuous materials, and you need a lot of gravity to hold onto them. Remember, the traction of force of gravity was gmm over r squared. The Earth can't hold on to a lot of hydrogen and helium, and it bleeds off into space. Something like a very large mass object like Jupiter or Saturn can hold on to a lot of hydrogen and helium because its gravity is larger. And this is really how Jupiter formed. So here we have the Sun, in this particular case, at the center of the protoplanetary disk, and lots of debris going around it. See all these little shadows from the rocky material. Now, all the other planets were going to form in this disk, but Jupiter itself was essentially a mini disk all to itself. So this is almost like a binary system forming. So this is the star forming, and this is a very big disk inside an even bigger disk. So this is Jupiter forming right here, and this is what it would look like. Essentially, it's a little version of the main disk that it's inhabiting. And then what would happen was you would have collisions and orbital resonances, and all of these bodies would interact gravitationally and collide and interact. So here we have collisions. So smaller planets, of which there were probably hundreds, all collided and bashed together and sometimes formed asteroid belts. It's likely what our asteroid belt is a failed planet, and some of them just smashed together and formed even bigger planets. And then eventually the whole system would stabilize, and we would end up with the solar system we know and love today. So you're really getting an ordered solar system out of chaos. And that's how our planets would come from. And then you've got a few leftovers. Comets and asteroids are basically left over what we call planetesimals, not big enough to make true planets out of, but small rocky bodies. So asteroids are rocky because they formed inside the frost line. Comets are icy because they formed outside the frost line. And then, as I said before, we had some surplus gas that was just essentially making the whole solar system very soupy, and we really wanted to get rid of that. So here's the solar system in the center, and here's the various planets going out from the sun. And then when the sun switched on and started to produce energy, it blasted out solar radiation and cleared away all of the excess gas. So soupy solar system cleared away by the solar wind. So that's where everything basically came from. We do have estimates of the age of the solar system, and the question usually is, how do we estimate the age of the solar system? Well, we can actually look at the Earth itself. We're living on a member of the solar system, which is really useful. And we can look at the age of the components that make up the Earth. So if we take some of Earth's rocks and we look at the radioactive decay of the elements in Earth's rocks since the Earth was formed, we can actually see how long they have been present. So some elements will naturally decay to produce other elements through radioactive decay. And the abundance of specific elements will tell you the age of the object you're looking at. So in this particular case, we're looking at, say, potassium. And the potassium is going to actually disappear, and it's going to produce argon. So here we've got a graph of argon. So fractions of argon are going up, fractions of potassium are going down. So we're looking at a rock and seeing how much radioactive potassium we have and how much radioactive argon is present. We can figure out when the rock formed. And our estimates basically tell us that the planets began to accrete in the solar nebula about 5 billion years ago. And that's an age that's based on the radiometric dating of old meteorites. Radiometric meaning radiation measurements from rocks, looking at the daughter molecules and the radioactive decay of rocks in the meteors or asteroids, or even on the Earth. So take a look at figure 625 that I just showed. It's on page 164, and you can sort of pore over that and have a look at the amount of argon that's produced with the decay of potassium. So by looking at the decay of potassium and the increase in argon, we can tell how old rocks are. The ages based on meteorites are actually quite useful. So we can do it with the Earth, we can do it with meteorites. The reason meteorites are useful is because they formed away from the Earth. So we're getting a comparison with other objects that hit the Earth. So meteors and comets are basically leftover remnants from the formation of our solar system. If you think about rocks on the Earth, we've had geological processing. We've had molten rocks and earthquakes and tectonic activity that's modified our rocks. If we get a meteor, which is a rock from space, landing on the Earth, or we look at an asteroid, then we can actually get pristine material that hasn't been reprocessed through some geological activity. Yes, the sun has affected it somewhat and the environment of space, but that's a very slow process compared to what the Earth does to its rocks. So meteors and comets are basically your remnants that are left over, and they haven't been altered. So they're very pure samples. So the meteors are as they were about 5 billion years ago, back at the beginning of the solar system. So what people do is actually go around places like Antarctica and look on the white pristine snow for black objects. And those black objects usually wind up being meteorites. And I should clarify a point that there's a lot of terminology that people often get mixed up. If you look into the sky, what you see in the sky when you see that streak, that shooting star, that is a meteor. When it hits the ground, it becomes a meteorite. A rock that is recovered from the ground is a meteorite, if it's fallen from the sky. If it's floating through space, it's technically a meteoroid. And the reason they're called meteors, this confused a lot of people, meteorology is the study of the weather. When people first started talking about this phenomenon, they were thought to maybe be some form of lightning, which turns out are completely wrong. So meteors, or shooting stars, if you go out into the sky, go outside and look at the sky, you can see these either sporadically, or there are actually specific seasons for meteor showers, such as the Lyrids or the Perseids or the Geminids. And what they are is rocks or sometimes dust hitting the outer atmosphere of the Earth and burning up. And you'll get a streak flash across the sky. And depending on the size of that meteor and what it's made of, depends how deep it penetrates into the atmosphere. If you ever see a green meteor, that's a meteor that leaves a green streak, that actually means it's ionizing oxygen, which means it's got quite far through the atmosphere. And there are a few types of meteor. This is a stony iron meteor. And what people often do is find these rocks and they'll cut them through in a segment and then polish the inside so you can see the detail. And you can actually see this is sort of a light coloured rock, and then you've got small traces of iron in it, all these little brown bits, and then you've actually got metallic iron inside that too. So that's where we'll end our discussion of the solar system, ages of the solar system, and we'll look at some exercises to do with this, and then next time we'll pick up talking about the actual planets in the solar system as they exist today and as they are.